Existence proofs using expectation. It is a common sense that the average of a set of numbers is never larger than the largest of those numbers. This is true for weighted averages as well as the following theorem shows. Theorem 15.21. Let x, which maps from omega to r, be a random variable so that the set S equals to the set x of u, such that u is in omega is finite, and let j be the largest element of S, then j, which is greater than or equals to the expectations of x. Proof using the definition of the expectations of x. E of x is equals to the summations of I times the probability where x is equals to I, summing for all I in S, which is less than or equals to j times the summations of probability of x equals to I, summing for all I in S, which is equals to j. We presented two applications of this idea. The first shows that a simple graph will always contain a large bipartite subgraph. Theorem 15.22. Let G be a simple graph with the vertex set n braces and m addresses. Then G contains a bipartite subgraph with more than m over 2 addresses. Proof. Let us split the vertices of G into two disjoint non-empty subsets A and B. Then A and B span a bipartite subgraph H of G. We omit the addresses within A and within B. Let omega be the set of 2 to the n minus 1, then minus 1 different bipartite subgraphs. We get this way. Let x of H be the number of addresses in H. On the other hand, let us number the addresses of G from 1 through m, and let xi equals to 1 if the hi has one vertex in A and one in B, and let xi equals to 0 otherwise. What is the probability of xi equals to 1? By our definitions, we can get a subdivision of m braces leading to xi equals to 1 by first putting the two endpoints of the hi to different subsets, then splitting the remaining n-2 element vertex set in any of 2 to the n-2 ways. Therefore, the probability of xi equals to 1 is equals to 2 to the n-2 divided by 2 to the n-1, then minus 1. And the probability of xi equals to 0 is equals to 2 to the n-2, then minus 1, divided by 2 to the n-1, then minus 1. This implies that the expectations of xi is equals to 0 times the probability of xi equals to 0 plus 1 times the probability of xi equals to 1, which is equals to 2 to the n-2, divided by 2 to the n-1, then minus 1, which is greater than 1/2. We can repeat this argument for all addresses. Then we note that x equals to x1 plus x2 plus x3 and so on plus xm. So theorem 15.18 implies that the expectations of x is equals to the summations of expectations of xi, summing with I starting from 1 to m, which is equals to m times the expectations of x1, which is greater than m over 2. As the expected value of the number of addresses in these bipartite subgraphs of G is more than m over 2, it follows from theorem 15.21 that there is at least one bipartite subgraph of G with more than m over 2 addresses. The next example is related to a well-known problem in complexity theory, the so-called Botrymius problem. Example 15.23. We are given a list L equals to L1, L2, L3, and so on until Lk of ordered triples, Li equals to Ai, Bi, and Ci, so that for any I, the numbers Ai, Bi, and Ci are distinct elements of n braces. It is possible, however, that symbols with different indices I and j denote the same number. let P equals to P1, P2, P3 until Pn be an n permutation. We say that P satisfies Li if the entry Bi is between Ai and Ci in P. It does not matter whether the order of these three entries in P is Ai, Bi, Ci or Ci, Bi, Ai. Prove that there exists an n permutation P that satisfies at least 1/3 of all Li in any given list L. Solution. Let Y be the indicator variables of the event that a randomly chosen n permutation satisfies Li. Then the probability of Yi equals to 1 is equals to 1/3, as each of Ai, Bi, and Ci has the same chance to be in the middle. Therefore, the expectations of Yi is equals to 1/3. Now, if Y is equals to the summations of Yi, summing for all index I starting from 1 to k, then Y is the number of Li in L that are satisfied by P. Theorem 15.18 then implies that the expectations of Y is equals to the summations of the expectations of Yi, summing with I starting from 1 to k, which is equals to k over 3, and our claim follows from theorem 15.21.